The Higgs, over here on the left, has a large mass and breaks the symmetry of this electroweak pattern. It makes the weak force very weak by giving the weak particles a large mass. Since this massive Higgs sits along the horizontal direction in this diagram, the photons of electromagnetism remain massless and interact with electric charge along the vertical direction in this charge space. So the electromagnetic and weak forces are described by this pattern of particle charges in two-dimensional space. We can include the strong force by spreading out its two charge directions and plotting the charges of the force particles and quarks along these directions. The charges of all known particles can be plotted in a four-dimensional charge space and projected down to two dimensions like this so we can see them. Whenever particles interact, nature keeps things in a perfect balance along all four of these charge directions. If a particle and antiparticle collide, it creates a burst of energy and a total charge of 0 in all four charge directions. At this point, anything can be created as long as it has the same energy and maintains a total charge of 0. For example, this weak force particle and its antiparticle could be created in a collision. In further interactions, the charges must always balance. One of the weak particles could decay into an electron and an antineutrino, and these three still add to 0 total charge. Nature always keeps a perfect balance. So these patterns of charges are not just pretty. They tell us what interactions are allowed to happen. And we can rotate this charge space in 4 dimensions to get a better look at the strong interaction, which has this nice hexagonal symmetry. In a strong interaction, a strong force particle, such as this one, interacts with a colored quark, such as this green one, to give a quark with a different color charge, this red one. And these strong interactions are happening millions of times each second in every atom of our bodies, holding the atomic nuclei together. But these 4 charges, corresponding to 3 forces, are not the end of the story. We can also include 2 more charges corresponding to the gravitational force. When we include these, each matter particle has 2 different spin charges, spin up and spin down. So they all split and give a nice pattern in 6-dimensional charge space. We can rotate this pattern in 6 dimensions and see that it's quite pretty. Right now, this pattern matches our best current knowledge of how nature is built at the tiny scales of these elementary particles. This is what we know for certain. Some of these particles are at the very limit of what we've been able to reach with experiments. From this pattern, we already know that particle physics at these tiny scales, the way the universe works at these tiny scales, is very beautiful. But now I'm going to discuss some new and old ideas about things we don't know yet. We want to expand this pattern using mathematics alone and see if we can get our hands on the whole enchilada. We want to find all the particles and forces that make a complete picture of our universe. And we want to use this picture to predict new particles that we'll see when experiments reach higher energies. So there's an old idea in particle physics that this known pattern of charges, which is not very symmetric, could emerge from a more perfect pattern that gets broken, similar to how the Higgs particle breaks the electroweak pattern to give electromagnetism. In order to do this, we need to introduce new forces with new charge directions. When we introduce a new direction, we get to guess what charges the particles have along this direction, and then we can rotate it in with the others. If we guess wisely, we can construct the standard charges in 6 charge dimensions as a broken symmetry of this more perfect pattern in 7 charge dimensions. This particular choice corresponds to a grand unified theory introduced by Petit and Salam in 1973. When we look at this new unified pattern, we can see a couple of gaps where particles seem to be missing. This is the way theories of unification work. A physicist looks for larger, more symmetric patterns that include the established pattern as a subset. The larger pattern allows us to predict the existence of particles that have never been seen. This unification model predicts the existence of these 2 new force particles, which should act a lot like the weak force, only weaker. Now we can rotate this set of charges in 7 dimensions and consider an odd fact about the matter particles. The second and third generations of matter have exactly the same charges in 6-dimensional charge space as the first generation. These particles are not uniquely identified by their 6 charges. They sit on top of one another in the standard charge space. However, if we work in 8-dimensional charge space, then we can assign unique new charges to each particle. Then we can spin these in 8 dimensions and see what the whole pattern looks like. Here we can see the second and third generations of matter now, related to the first generation by a symmetry called triality. This particular pattern of charges in 8 dimensions is actually part of the most beautiful geometric structure in mathematics. It's a pattern of the largest exceptional Lie group, E8. This Lie group is a smooth, curved shape with 248 dimensions. Each point in this pattern corresponds to a symmetry of this very complex and beautiful shape. One small part of this E8 shape can be used to describe the curved space-time of Einstein's general relativity, explaining gravity. Together with quantum mechanics, the geometry of this shape could describe everything about how the universe works at the tiniest scales. And the pattern of this shape, living in 8-dimensional charge space, is exquisitely beautiful. And it summarizes thousands of possible interactions between these elementary particles, each of which is just a facet of this complicated shape. As we spin it, we can see many of the other intricate patterns contained in this one. And with a particular rotation, we can look down through this pattern in 8 dimensions along a symmetry axis and see all the particles at once. It's a very beautiful object. And, as with any unification, we can see some holes where new particles are required by this pattern. There are 20 gaps where new particles should be, 2 of which have been filled by the petit Salam particles. From their location in this pattern, we know that these new particles should be scalar fields, like the Higgs particle, but have color charge and interact with the strong force. Filling in these new particles completes this pattern, giving us the full E8. This E8 pattern has very deep mathematical roots. It's considered by many to be the most beautiful structure in mathematics. It's a fantastic prospect that this object of great mathematical beauty could describe the truth of particle interactions at the smallest scales imaginable. Now, this idea that nature is described by mathematics is not at all new. In 1623, Galileo wrote this: "Nature's grand book, which stands continually open to our gaze, is written in the language of mathematics. Its characters are triangles, circles, and other geometrical figures, without which it is humanly impossible to understand a single word of it. Without these, one is wandering around in a dark labyrinth." I believe this to be true, and I've tried to follow Galileo's guidance in describing the mathematics of particle physics using only triangles, circles, and other geometrical figures. Of course,